Okay, welcome back for our next session on macular pigment. I'm Liz Johnson from Tufts University, and I will be presenting, where is he? John Landrum will be speaking on macular pigment, and that's really appropriate since he was one of the first to identify macular pigment along with Richard Bone. And so he's going to be giving us some of the history of which he's a part. And any publication you see on macular pigment will include John Landrum. And he comes to us from Florida International University. And then we're going to be hearing from Billy Wooten. And after we learned about what macular pigment is, he's going to tell us how to measure it, the different various measures of macular pigment. And he, too, is part of the history of macular pigment. I remember when I first met Billy, it was at Max Snodderly's lab, and it was about 15 years ago, and I saw this black shoebox, it looked like to me, and it really was like the first incarnation of this macular pigment densitometer, and he's going to be talking about what that how that's come along and how it's measured. And then he comes to us from Brown University, and then we'll be ending up with John Nolan. So we'll learn about what macular pigment is, how to measure it, and he's going to be talking about measures macular pigment mesozeaxanthin, which is another one of the macular pigment. And he comes to us from Waterford Institute of Technology. So I've introduced them all, so I won't do that again as they get up and talk, and we'll start out with John Landrum.
Well, good morning. It's such a pleasure to be here in Cambridge, and I'd like to thank the Howards for this fine venue and the invitation to be here. And I thought I'd put in a couple of photographs of our home area. There's Miami, and you can see that God is in action there. There's a lot known about Miami, and here's better days. So we're very pleased to be here and enjoy Cambridge and see some of the things that are going on here. I thought it would be really fun to look back, way back, and retrospectively look at where macular pigment has come over the years. So I thought it would be nice to go back. Francois Delory published a nice paper where he summarized the history, and I've gone back and I've picked up some of the sites, and you know, this macular pigment isn't such a new thing after all, really. About the period of the French Revolution, the period of the American Revolution, we find that is when the first reports are of macular pigment. And at that time, if you read right up here at the top, Everard Holmes says, an account of the orifice in the retina of the human eye, and discovered by Sommering, but there's an earlier report of Francesco Buzzi, but you know, all simultaneously, essentially, from our perspective. So macular pigment really has kind of a somewhat more distant history than most people are aware. And so this is the cover page from Everard Holmes' report on this talk. So it was read April 19, 1798 to the Royal Society. So very interesting that we're almost back in the same locale as where things began. Macular pigment wouldn't have progressed very far if we didn't learn to look in the back of the eye. And so I think to skip over Helmholtz and his contribution of the ophthalmoscope would certainly be a mistake. And it's just remarkable to note that these individuals like Helmholtz were so diverse in their contributions to science and generally making things move forward for us. And James Clerk Maxwell, again, you know, one of those landmark contributors to physical sciences, fascinated by color vision. And we see here a manuscript, and this one comes from the U.S. Bureau of Standards. That's where we got the copy. But notice right up here, there's initial JCM. It was a copy that had been transmitted to someone and then donated to the Standards Library. So kind of fascinating. So he published on the unequal sensibility of the foramen centrale to light of different colors. So, you know, the idea that the macular pigment was affecting color vision came along very early. This is the very first color photograph ever made, made by Maxwell. Somewhat earlier, these are not all in chronological order, we have Hedinger, who is talking about perception of polarized light. And this was one of the things that first interested me in macular pigment, because Richard Bone, my colleague for so long at Florida International University, was very fond of getting out a polarizer and saying, look, you can detect polarized light, you know. And so, you know, I was always fascinated by that and said, well, how is that? And he said, well, there's this pigment in the eye. And we both arrived at Florida International University. Well, let me go back. We both arrived at Florida International University in 1980. And so we began to collaborate. But this is Hedinger's brushes, and it's the result of the absorption of polarized light by the macular pigment. And this works in the following way. The axons of the nerves in the retina contain pigment. The pigment molecules are elongated, and so they will only absorb light that is polarized along their axis. And so if we have horizontally polarized light coming in, only these axons here will absorb the light, while these will not. And so you get a shadow on the photoreceptors, and that is the Hedinger brush phenomenon. So that has been known since 1844. We've had a great deal of knowledge about the macular pigment for a very long time, and yet it's only in really more modern times that we've gotten into the details of what is the macular pigment. And so this photograph is circa 1980, Malinois. I think the particular photograph was taken by Martha Nuringer and Max Snodderly. It's of a macaque retina, and very clearly you see the yellow spot here in the center of the macula. Max also took these cross-section, and you're going to see these again and again, I hope, because these are remarkable photographs. Max took these cross-sectional photographs. It's really only one photograph, but in three different lights. Here in white light, you clearly see the yellow pigmentation in the inner section of the retina, and you do see pigment extending down toward the photoreceptors. I think that's very important. Under blue light, that's much more discernible, and so we see very clearly here what's going to be repeated again and again and again throughout the week, and that is that macular pigment absorbs blue light very, very intensely. Green light, not so. Red light, not so. So this is also its ability to affect color matching in the central eye. So what is the macular pigment? The first real effort in this direction was made by George Wald, and most of you are aware that George Wald received the Nobel Prize for his identification of the role of vitamin A in the photo pigment, and yet he also was interested in everything else about the eye, and so he published this in 1945. We see the spots are a measurement of the pigment by sensitivity. So this is a macular pigment measurement back 1945. The dotted is an extract of lutein from leaves, and the solid line here is the xanthophyll extracted from about 10 retinas. So he took a spectrum at that time and was able to say, I think it's lutein and possibly it's cis isomers. The reason have cis isomers present, you lose the resolution between those bands that make up the typical carotenoid spectrum, that three-peak structure. So this is at 1945, and things stayed about the same until the early 1980s. Now let me remind you about what carotenoids are. Carotenoids are plant pigments. They're synthesized only by plants. They are not something that higher animals can synthesize de novo. We can modify them. We can oxidize them. We can cleave beta-carotene and make vitamin A, but we cannot synthesize them. So here's beta-carotene. They are long conjugated polyene structures. This is what's responsible for their color. The colors of the carotenoids vary from yellow to red. And here's lycopene. The difference that we see in lycopene is that it does not have a ring. So we see ring and acyclic carotenoids, but they all characterized by this polyene structure. So what is the identity of the macular pigment? Well, Wald got it right. There is lutein in the macular pigment. In the early 1980s, Richard Bone and I began to collaborate, and we thought this would be a straightforward little problem. There's a pigment, it's a chemical problem, we have great new tools, and we would be able to identify this. Extracts of the macular pigment showed that there were two essentially pure products. They were carotenoid in nature. On 3 different chromatographic systems, they would separate with different retention times. We could take extracts from pure plant sources, which were identified as lutein and zeaxanthin, and they matched retention time for retention time on the different materials. Their spectra matched lutein and zeaxanthin, and we published what we called a preliminary identification of the macular pigments. Somewhat later on, we were able to definitively nail down this identification and publish a mass spectrum. So these carotenoids are lutein and zeaxanthin in the macular pigment. And what was striking was that Wald had missed the zeaxanthin, because how could he miss something? But he didn't have HPLC. And that's the answer. The advent of HPLC allowed us to do something he could not. And so we were able to add to the knowledge about the macular pigment at that point. And so these are the structures. Notice the structures are very much like beta-carotene down here on the bottom and alpha-carotene up at the top. But the presence of hydroxyl groups on the end rings changes the polarity of these molecules and makes them non-vitamin A carotenoids. Their spectra are remarkably similar one to the other. So they are, for all intensive purposes, identical yellow pigments. You couldn't look at 2 solutions and by eye easily distinguish these 2 carotenoids. So let's look at something that was interesting to us a little later on. We began to wonder, because clearly the pigment is greatest in the central retina. It's yellow there to the eye, but is there pigment further out in the retina? And we heard some discussion of what about the pigment out in the periphery? How does it affect flicker photometry? And so we can answer some of that question now. If you take the central bullseye and then the rings around the macula and you chromatograph, you see the carotenoid peaks, which are right here, and right here, are easily detectable. And in the central retina, zeaxanthin dominates over lutein. But as you move to the medial and then the outer ring, this reverses in abundance. And so in the peripheral region, there is carotenoid, and there is really an abundance, and when you take the increased area, it's very easily measured, but it's not optically detectable when you look at the retina. And the zeaxanthin is less abundant in the periphery, more abundant than lutein in the central area. Dietarily, lutein is the most abundant of these carotenoids. As we've heard, there are about 50 carotenoids in our diet, probably 15 or 16 in the serum normally, and only these 2 in the retina. And not only that, but there's a remarkable distribution difference from one part of the retina to the other. So here they are again. And at this point, I want to emphasize the double bond at this end of the ring is in a different place than that one. So zeaxanthin and lutein differ in the position of a double bond and the geometry of a hydroxyl group. That hydroxyl group is folded back away from us. This hydroxyl group is folded out towards you. So the 3-dimensional shape of the molecules is a distinguishing quality that we need to keep in mind. So here's this distribution. There's the macular pigment in this wonderful, I've used Miami colors here, right? So bright purple here. It should have been pink for the flamingos, but peaking in the central fovea. Now here's the distribution that we need to think about. Lutein, most abundant, between 2 and 2.5 to 1 out here. In the serum, the ratio is more like 3 or 5 to 1. So that's interesting. It's not identical to the serum. As we move into the central fovea, the ratio inverts. Here's 1. At the central part of the fovea, the ratio is now about 0.25. And so we have really a dramatic inversion of the ratio. Why is that? What's going on? How does a human body identify the difference between those two molecules that we saw the spectra? They're identical. We saw the structures. Any uncareful, quick review of those, you'd say those were the same two structures. How does the body identify and distinguish those two and put them in the right place? Well, that's going to be the whole theme of my talk. Well, the answer turns out, in part, we do it by metabolism. So, there happens to be another carotenoid in the retina that I didn't tell you about. There's lutein from higher plants, there's zeaxanthin from higher plants, and there's mesozeaxanthin, which is formed in the retina by conversion from lutein. And we know this because Liz Johnson tells us so. And I'll show you that in a moment. But if we look at a macaque retina and we analyze it using a technique called chiral column chromatography, this will resolve stereoisomers. So remember I told you the hydroxyl group in one points this way, the hydroxyl group in the other points that way. This is the stereogeometry of the carbon centers. And there are 3 different chemical structures for zeaxanthin based on this geometry of the hydroxyl groups. There is RR zeaxanthin formed in higher plants. There turns out to be RS zeaxanthin, which we call mesozeaxanthin, which we now know is formed in the retina. And there is SS zeaxanthin, which is not talked about very much, but is also present in the retina. Tiny amounts, but there it is. So in a macaque retina, we see lutein, zeaxanthin, and mesozeaxanthin. Mesozeaxanthin and zeaxanthin are about in equal abundance in this mature macaque retina. So what is going on with the distribution of the carotenoids? Well, there's the central pigment. Here's the ratio. This is where zeaxanthin dominates. If we map mesozeaxanthin to zeaxanthin ratio in here, we find that in the central part of the retina, mesozeaxanthin is most abundant. That's the place it's produced most. So what's going on is we believe, and we proposed, a conversion of lutein to mesozeaxanthin, which is not occurring very efficiently out here, but is occurring very efficiently in here. And as lutein converts to zeaxanthin, this ratio should, of course, change because lutein decreases, zeaxanthin increases. And the ratio is quite sensitive to that. So that was shown by Liz Johnson, Martha Nuringer, Rob Russell, Wolfgang Schalk, who's here, and Max Snodderly. And they fed deficient monkeys that were raised deficient on these carotenoids, both lutein and zeaxanthin, and then analyzed the retinas of those animals, and only the, and I'm sure Liz is going to talk to us about this later. A little bit? Good. Okay. So only in the lutein animals did we see mesozeaxanthin produced. And that was just startling, really remarkable results. So what are the structural differences between these molecules? They look the same. Are they really different? How different are they? Can we understand something by looking at them? Well, in this slide, the half on the left is identical in both molecules. It's only the whoa, watch those things go. It's only the pigmented region that's the same. The double bond is here at 11 o'clock versus 9 o'clock. The hydroxyl group in zeaxanthins out towards you. The hydroxyl group Lutein is back away from you. So those are the differences. In mesozeaxanthin, the hydroxyl group is like that rather than like that. So that's the distinction there. And so let's look at lutein and zeaxanthin three-dimensional structures. Again, the bottom part's the same in both molecules. But looking at the ring up at the top, you see the hydroxyl group right here. I know it's tiny, but it's pointed right up to the ceiling. Look at the hydroxyl group over here. It's off-center, and it's pointed off sort of over to 11 o'clock. So it's not a very large difference, but it's a significant difference. And so we need to think about that, and we need to understand how could that give rise to recognition. Paul Bernstein's going to talk about the identification of proteins and binding of proteins and the accumulation of carotenoid in the retina by these. And so think of this in terms of how these molecules bind. Now, this bond right here connects the ring to the chain. And the ring can rotate around as though it were on a bearing. And so one of the questions that chemists will worry about is how easily can that twist around? Is there any rubbing or bumping? You know, if your tires aren't balanced, your car won't ride real well. And so we worry about that in these molecules. So in the previous case, this is the zeaxanthin end group. And see, the hydroxyl group is right out there. In this next case, this is the lutein end group, and see, this is a little off-center, so it's like a wheel out of balance. This is another view of the same thing, showing that same out-of-balance position of the hydroxyl group here. So let's look at a little movie and see if we can sort of, whoa, we've got to go back. See how that rolls around, and here, you know, it's sort of like the tire off balance. Here it's sort of on balance. So lutein, the hydroxyl group's way off to the side. So we can imagine in the protein where that lutein ring structure binds, there's going to be some hydrogen bonding out there. We know, right, Watson-Crick, you know, or this is the home of the great discovery, the hydrogen bonding that's at the center of the DNA. This hydrogen bonding is almost certainly critical to the binding of these molecules in proteins as well. And so the location of the hydrogen bonding group that holds the lutein or zeaxanthin in the protein is going to be a slightly different place. And so we see that this is a good way to distinguish between these molecules. I'm going to skip over the next slides a little bit because we really don't want to talk about ab initio calculations very much today. But the blue is the zeaxanthin ring and the rotation of that. That's a narrower barrier to rotation. The orange is the epsilon ring of lutein. It's a higher barrier, but what I want you to understand here is although the zeaxanthin ring, the beta ring, spins more easily, less bumping, this barrier is only 9 kilocalories per mole. In scientific jargon, that's just a little hill. That's very easy. At room temperature, these two molecules are completely mobile. They can twist around and reorient themselves to fit into a molecule as need be. So the lutein ring can swing around to find its hydrogen bonding pair in the protein that it binds to. And so that's very significant. It's not rigidly struck. So that's important. Another feature of the molecule is that the ring in lutein is over like this, you know, from like those Egyptians, right? Whereas the ring in zeaxanthin is up like that. So if I do this, we call that flex, right? If you flex your wrist. So we're now talking about flex angle between these. Before we were talking about rotation. Now we're talking about flex. So so the angle here is about 107 for lutein, almost 90 degrees, and 170 for zeaxanthin. Don't worry about this. This is a very busy graph, but this angle is the flex, okay? So over here is zeaxanthin. Zeaxanthin, no matter how you rotate the ring around, it's always about 180 degrees right on the polyene. Lutein, no matter how much you rotate the end group around, it's always around 107. So if you want to flex or extend lutein, this is the energy required, about 10 kcals, maybe 12. If you want to flex zeaxanthin, the energy is much more dramatic. It's about 30. So it turns out that sticking zeaxanthin into a place where it has to flex over like this would cost you a huge amount of energy. This is clearly a way a protein can distinguish between these two molecules. Lutein can fit into an L-shaped wedge space, but zeaxanthin cannot. Strikingly, lutein can fit into an open space where it has to fold up if it needs to do so. So there's a little more flexibility. Well, we talked about mesozeaxanthin, and I don't want to leave mesozeaxanthin out of the story. So up here at the top is mesozeaxanthin. Down here at the bottom, look at the hydroxyl groups on RR zeaxanthin. They essentially are like this, whereas mesozeaxanthin's more like that. So again, there's structural distinction between these two molecules. Now, I keep telling people that I think we evolved on the savannas in Africa. The macular pigment is a characteristic of primates, and so the primates were developing macular pigment a long time ago. But to my knowledge, rich sources of zeaxanthin seem to be all New World plants. And I don't know if that's going to hold up, but it seems to me that it would be very worthwhile if zeaxanthin were a potent antioxidant that were useful to you, for you to be able to make it. Since you can't make de novo the carotenoid, maybe it's because of deficiency in the diet that we developed a method to convert lutein to mesozeaxanthin. It's kind of far out there as a hypothesis, but at least it gives us some idea of what the evolutionary drive might be. What are the functions of the carotenoid? We've also heard a little bit about those. We saw that the carotenoids absorb blue light. We've heard them referred to as antioxidants. Wolfgang, I'm sure, is going to talk about this later on. Wolfgang Schalk. This is work done by Felix Barker. And in this case, a laser was directed at the back of the eye, and lesions were produced. And these are in macaques, not people. And these lesions are of larger size if the exposure is for a longer time. More light, more lesion. Note that the size of the lesion is smaller in the pigment area of the retina, consistent with attenuation of the blue light, and consistent with an antioxidant potential for the carotenoid in that region. So it seems that there's clear evidence for an acute protective role for these pigments. That would be good enough, wouldn't it? But there's also the realization that day in and day out, we go outdoors, we see the blue sky, the sunlight, and a little bit of damage is occurring all the time. We know about the buildup of drusen throughout life. We know about the photooxidative processes. So the pigment will protect from photooxidative damage in the central retina. There's no question that that is the case. There's clear evidence of that now. So is there a correlation with a reduced risk for AMD? And Julie was so kind as to put this slide in her talk earlier. And we struggled with this, but how do you understand what's going on? Because in the macula, you have degeneration going on. And if you have less pigment, is it the chicken or the egg? Has the pigment level gone down because you've got degeneration and loss of pigment to a degenerative process, or did the degeneration occur because you had lower pigment? Well, so we looked out further in the retina. We thought, if you look to places in the retina that are less susceptible to the damage that's going on, you might be able to get an answer. And we had 56 paired eyes, and what we saw was that in every case, the AMD at all sections of the retina was lowered. And the statistics, and I will not claim to be a great statistician, but the statistics do indeed show that this is at the level of significance. So the outer regions of the retina, the low levels of pigment, do predict the risk associated with AMD. Dietary modulation. So if the pigment can protect the eye, if it does protect the eye, and if you don't have it, how can you get it? Can you eat more? Can you make yourself at lower risk? We already know we can deplete the retina. Martha Nuringer has studied the monkey troops in Oregon and shown that you can deplete the retina. Can we increase this? So about 1995, Richard Bone and I attended a Gordon conference, and there was a gentleman from Cambridge, England there, and we were talking to him about maybe we could do a study where we could get lutein. This was Dr. Howard. And he was so kind as to supply us with a little bit of marigold resin, which is an ester of lutein. And this is very much like peanut butter substance. And we diluted it in canola oil and subsequently took 30 milligrams a day. And this is the result of our serum response to that 30 milligram dose. It's a very clear response to the dose. And then at the end of supplementation, just as you would expect, the level drops off dramatically. Macular pigments were something we could measure in our lab. Richard Bone had a very nice flicker photometer. And at about day 40, we were about to end the experiment, because after 40 days, if nothing's happening, 40 days and 40 nights, he got to have some sunshine. Well, we were getting tired of eating this oleoresin stuff. But we continued on a bit longer, and lo and behold, we went through a flat zone, and then we saw an increase. Remarkably, at the end of supplementation, the increase does not stop. Well, hold it. Cause and effect, right? Well, look, at the end of supplementation, your serum level is still pretty high. It's 200 days, and you're still not at baseline. So for quite a while after you discontinue a high supplementation on an acute dosing basis, you're going to have a response in the macula. Notice that the increase was essentially linear, and notice that unlike the serum level, we didn't see a drop-off, we saw a maintenance. That we thought was striking. That once you produce high levels in the retina, they are maintained. And so it's been our experience that this is for a very significant period of time. We've studied doses, and you see here that doses go up. We were talking earlier, Julie was talking about subjects kind of getting enthusiastic about their study. Well, look at the placebo. This is baseline. This is at the end. Now, those are not statistically different, but the placebo folks got enthused by being in a study, and they ate better. Their serum levels went up. Not so much, though, if you ate 5 or 10 or 20 milligrams. Notice baselines in all 4 groups are the same. So there's a dose-response relationship, and this has been confirmed by other groups, and so I think that's now a well-accepted relationship. There are some problems with the quality of formulations in various products. There are good formulations out there, and there's not so good formulations, and one has to watch out for that. So simply because you're buying a product with lutein or zeaxanthin in it, it doesn't mean your serum level is going to be responsive at high levels. In 1988, we did look at each decade of life in macular pigment, and we were able to look at young eyes, and we had some young eyes in the 1 to 2 age group. Strikingly, the lutein zeaxanthin, let me rephrase that, the zeaxanthin to lutein ratio was very low in these young eyes. At that time, we simply put this out in the paper and left it alone. The adult ratio, I've already told you, in the eye is such that zeaxanthin dominates over lutein, but at birth that's not so. We've been fortunate enough to look at macaque retinas, and so these are macaques. This is the zeaxanthin to lutein ratio of macaque animals versus year, and you see the ratio at birth is about 0.5. It increases over this time period, and there's a little scatter in the data, but I think none of the values are as low as at birth. That's a striking result. There is significant development going on in the early period in life. We're not born with a fully formed macula. The macula takes about 48 months to fully mature. The elongation of the rod outer segments is something that goes on, the packing of the cones together. And this is what the zeaxanthin ratio looks like in those macaques. So at birth, the macaques have very little, if any, mesozeaxanthin, but if we plot mesozeaxanthin over the first few years, it's an almost linear increase from birth on. So that's a striking piece of information. What's going on at birth that we need to start making mesozeaxanthin? And, you know, on the savannas, we didn't live to get macular degeneration. So what was macular pigment for in those days? Those are questions I hope Billy will talk to us about. And so I'd like to thank my collaborators, most of all Richard Bone, with whom, you know, all of this was done, and so, you know, co-equal on so much of this. So the calculations were done with some colleagues in the chemistry department. Martha was kind enough to supply us with the retinas. We published a collected book last year on carotenoids, and the reason I put that up is that I've invited many of the authors. John and I will be co-editing a new volume based on the proceedings that come forth from this meeting. So thank you all.